Okay, this is the second video in the playlist that deals with how attractive force can be used to explain atomic size and ionization energy. In the first video, we used attractive force to explain the trend of atomic size and ionization from left to right across any period on the periodic table. And in this video, what we're going to do is focus on what happens when we move down a group. Now, I want to draw your attention over here to the schematic on the right side of the screen. And this should help you rationalize the things that we're going to talk about. And it just represents how the energy levels where we place the electrons is related to where the protons are in the atom. So energy level 1 is the energy level that's closest to where the protons are. This is going to be electrons that are in N1 are going to be or have the lowest potential energy of any of the electrons in the atom because they're the electrons that are closest to the protons. All right, and what that means is that these electrons, the ones that are closest to the protons, are going to be the hardest electrons to remove. So they're going to have the highest ionization energies, and they are going to be the ones that also have that are the most stable and whose attractive forces are going to be of the highest that you find. And as we move from N1 into higher energy levels, those electrons are being moved further and further away from where the protons are. So I show the distance over here on the right. As we shift from N1, say, into N7, those electrons in N7 are going to be much further away from where the protons are. And consequently, these electrons will be easier to remove from the atom than electrons would be that are located in energy levels that are closer into the protons. This phenomenon I'm talking about is governed by Coulombs law. All right, and Coulombs law says the force of attraction between the protons and the electrons, and this is the simplest form of the law, will be equal to the product of the charges between the protons and the electrons divided by the distance, the square of the distance that the electrons are away from where the protons are. All right, so we're going to be talking about Coulomb's law as we go through this. Force of attraction, how tightly those outer electrons are being held. And this controls atomic size and ionization energy. All right, now, as we move down a group, let's talk about what happens with this. All right, and group number, so the group that we're focused on is group 1A, and this group consists of lithium, sodium, potassium, rubidium, and cesium. All right, and then to the left of the element symbol, I've indicated the period number where we are. And it would be helpful for the viewer to remember that period number is equal to energy level that is being filled as we move left to right across the table, across periodic table. All right, so it's crucial for the viewer to realize as we go down from lithium to sodium that we have shifted, our electrons have shifted out into a new energy level. Now, in the previous video, I introduced the concept of effective nuclear charge because there's two things we need to pay attention to here. All right, we need to pay attention to what's going on with the charge as we go down the group versus what's going on with distance. It's charge versus distance. So first I want to deal with the charge. And what we want to do is we want to calculate the effective nuclear charge on the outermost electrons of lithium. So remember that for lithium, it has 3 electrons. Its outer or its electron configuration is 1s2, 2s1. Its core electrons are here. we can actually, let me draw another picture of this. So if I put lithium's 3 protons in a circle, the first 2 electrons in energy level 1 are sitting between the protons that attract the electrons to the nucleus and the single electron that's sitting in the outermost shell. So this electron here that's out in the 2s shell. All right, and you see that these 2 electrons are sitting between the protons and this outermost electron in the valence of lithium. So we learned how to calculate the Z effective in the last video. It's equal to the core electrons, or excuse me, it's equal to the protons, which in this case are +3, minus the core electrons, which there are 2 of them. These guys right here. And that means that the effective nuclear charge that's attracting the outermost electron of lithium is +1. Now, what we want to do is see if this value changes when we move down to sodium. Because if you remember the last videos, we go left to right across the periodic table. This value, the effective nuclear charge, the amount of charge that is attracting those outer electrons to the nucleus increases left to right. So we need to know what it's doing as we go down a group. So we're going to calculate the effective nuclear charge for sodium. Now, the electron configuration for sodium, which I'm going to do very quickly because I think it will help the viewer, is going to be 1s2, 2s2, 2p6, 3s1. Okay, if we count the electrons that are here, we've got a total of 6, and 2 is 8, and 2 is 10 electrons, which represent the inner core of sodium, by contrast to its outermost valence electron. Outermost valence electron. So the Z effective for sodium is going to be 11 minus 10 equals +1. So check it out. Our effective nuclear charge as we go down a group is not changing. The viewer can calculate it for every single one of these elements as we move down a group. And this is going to be true all the way across the periodic table. So the charge as we move down a group is not changing. Charge not changing as we move down the group. But let's look and see what's going on with the distance factor. Check the distance out. So I want to come back over here to my diagram. All right, we started with lithium's outermost electron being in n equal 2. We go to sodium, and look what's happened. Its outermost electron is n equal 3. And then we go to potassium. Its outer electron is n4. And we go to rubidium. Its outer electron is n5. And we go to cesium and we see that its outer electron is n6. Look what's happened to my distance as we go here. Here's lithium. Here's sodium. Here's potassium. Here's rubidium. And here's cesium. As we move down any group in the periodic table, its outermost electrons are shifting into higher energy levels. The consequence of this is the distance is going up. Distance is going up. as we move down any group, the distance is going up. So your distance factor, delta D, is huge, changing, big change as we move down the group. So your force of attraction as we move down a group, force of attraction is going down because this distance square factor here is getting very large. The charge is remaining as we go down group 1, +1. So for group 1, the value in the numerator is going to be +1 as we go down the group. Keep in mind as we shift into a different group, this number is going to change, but it will remain constant as we go down the group. So charge remains constant as we go down any group. The distance is increasing dramatically because as we go down the group, each new electron is being added to a new energy level. And you can see from my diagram that as we shift from one energy level to the next, the distance is going up. So this explains the fact that atomic size is increasing down any group, and ionization energy, which I'm going to abbreviate, is decreasing. Ionization energy is decreasing as we go down any group because the distance factor has increased it so substantially, and these electrons that are located further away are easier to remove.